Hello there, and welcome to this quiet corner where big questions can unfold slowly and wonder is allowed to take its time. Tonight we're stepping away from the familiar, away from the everyday rhythms of life on Earth, and into something much larger and more unsettling. We're going to explore an idea that might change how you see our place in the universe, not just as individuals, but as an entire species. It's called the Great Filter, and it might be the most important concept you've never heard of. Not because it's complicated, though it touches on physics and biology and mathematics, but because it asks a question that sits quietly at the edge of everything we think we know about intelligence, about progress, and about whether we're truly alone. Picture this for a moment. You're standing outside on a clear night, looking up at a sky scattered with more stars than you could count in a lifetime. Each one of those points of light is a sun, many with planets orbiting around them. Some of those planets sit in what we call the habitable zone, where water can exist as a liquid, where the conditions for life, at least as we understand it, might be just right. Or the numbers are staggering. In our galaxy alone, there are somewhere between 2 and 400 billion stars. In the observable universe, there are roughly 70 sextillion stars. That's a 7 followed by 22 zeros. Even if life emerges on only a tiny fraction of the planets around those stars, we should expect the galaxy to be teeming with civilizations. Some younger than us, some older, some perhaps millions or billions of years ahead of us in their development. And yet, when we listen to the cosmos, when we point our most sensitive instruments toward the stars, when we search for any sign of intelligence beyond our own, we hear nothing. Silence. The universe appears, for all intents and purposes, empty of other minds. This is what scientists call the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a question that has haunted astronomers and philosophers for decades. Given the sheer scale of space and time, given the billions upon billions of opportunities for life to arise and evolve, why haven't we encountered anyone else? The Great Filter offers one possible answer, and it's not a comforting one. The idea suggests that somewhere along the path from simple chemistry to galaxy-spanning civilization, there exists a barrier so difficult to overcome that almost no species manages to pass through it. A filter so great that it stops the vast majority of potential civilizations in their tracks, leaving the universe largely silent and empty. The concept was first formally outlined by economist Robin Hanson in the 1990s, though the underlying questions had been troubling scientists for much longer. Hanson laid out what he saw as the critical steps in the development of any technological civilization. The right kind of star system, with the right mix of elements and stable conditions. The emergence of self-replicating molecules, the spark of life itself. The evolution from simple cells to complex ones, from single-celled organisms to multicellular life, from basic multicellularity to intelligent multicellularity. Then comes the development of what we might recognize as intelligence, the mastery of tools and fire, the emergence of technology, and finally, if a species makes it that far, the expansion beyond their homeworld to become a spacefaring, perhaps galaxy-colonizing civilization. Each of these steps represents a potential bottleneck, a place where the Great Filter might be hiding. And here's where the concept becomes deeply personal, even existential. Because if the filter lies behind us, in our evolutionary past, then we might be extraordinarily lucky survivors. We might be among the rare few who manage to slip through. But if the filter lies ahead of us, if the most difficult step is yet to come, then our future as a species might be far more precarious than we imagine. The location of the Great Filter has profound implications for how we should view our cosmic solitude. Oxford philosopher Nick Bostrom has pointed out one of the most counterintuitive aspects of this entire discussion. He argues that in the context of the Great Filter, no news is quite literally good news. the continued absence of detected extraterrestrial life might actually be the best possible outcome for humanity's long-term survival. This sounds backwards at first. Shouldn't we hope to find life elsewhere in the universe? Shouldn't the discovery of other civilizations be cause for celebration? Not necessarily, says Bostrom, because every time we find evidence of life successfully passing through one of those evolutionary steps, it suggests that particular step isn't where the Great Filter is located. And if the filter isn't behind us, it might very well be ahead of us. Consider what it would mean if we discovered microbial life on Mars. That would suggest that the origin of life itself, the transition from chemistry to biology, isn't particularly rare or difficult. If we found fossils of complex multicellular organisms, it would mean that several more steps can be passed relatively easily. Each discovery would narrow down where the Great Filter might be hiding. And if we ruled out all the steps in our past, we'd be left with the most unsettling possibility of all, that the filter lies in our future. Bostrom has said that finding fossilized complex life on Mars would be, by far, the worst news ever printed on a newspaper cover, because it would suggest that the Great Filter is almost certainly ahead of us, virtually guaranteeing our eventual extinction as a technological species. This creates what might be the strangest scientific hope in human history. We find ourselves in the peculiar position of hoping that life is rare, that intelligence is extraordinarily difficult to achieve, that we are, in cosmic terms, incredibly special. Not because we want to feel important, but because the alternative, that we are ordinary and that our future is likely to end in failure, is almost too difficult to contemplate. But what might this Great Filter actually be? Where along the path from chemistry to civilization might the barrier be located? The possibilities are as fascinating as they are troubling, and they span everything from the deepest biological processes to the most advanced technologies we can imagine. One of the most commonly proposed locations for the Great Filter is at the very beginning of life itself. Abiogenesis, the process by which living organisms arise from non-living matter, remains one of the most profound mysteries in science. We know it happened at least once here on Earth, roughly 4 billion years ago, but we don't fully understand how. The challenge is immense. Life, even in its simplest forms, requires an extraordinary level of complexity and coordination. DNA stores information, proteins carry out functions, membranes maintain structure, and all of these components must work together in precisely the right way. It's a chicken and egg problem of staggering proportions. You need DNA to make the proteins that replicate DNA, but you need those proteins to read the DNA in the first place. Neither can exist without the other. Yet somehow, both had to emerge from purely chemical processes. For decades, scientists have struggled to understand how this transition could have occurred. Various theories have been proposed. Perhaps life began in tidal pools, where cycles of wet and dry conditions could have concentrated organic molecules. Maybe it started near hydrothermal vents on the ocean floor, where chemical energy was abundant. Some researchers have suggested that clay surfaces might have provided the template for early replication, or that ice-covered lakes could have created the right conditions for complex chemistry to emerge. Despite all this research, we still don't have a complete, step-by-step explanation for how life began, and that uncertainty leaves open the possibility that abiogenesis is extraordinarily rare, perhaps so rare that it represents the Great Filter that has kept most of the universe lifeless. But there's a complication with this idea. Life on Earth appears to have emerged remarkably quickly after conditions became favourable. Our planet formed about 4.5 billion years ago, and the earliest evidence of life dates back to at least 3.8 billion years ago, possibly even earlier. In geological terms, that's almost immediate. As soon as Earth cooled enough and the right chemical ingredients were available, life seems to have appeared. This rapid emergence might suggest that abiogenesis, while complex, isn't actually the Great Filter we're looking for. If the origin of life were truly rare, we might expect it to have taken much longer to occur, or to have required multiple attempts over hundreds of millions or billions of years. Instead, it happened quickly, almost as if it were inevitable, given the right conditions. If the Great Filter isn't located at the origin of life, then perhaps it lies in one of the later evolutionary transitions. The development of complex cells, for instance, represents a fundamental leap in biological organization. All life on Earth can be divided into two basic categories: prokaryotes, which include bacteria and archaea, and eukaryotes, which include everything else: plants, animals, fungi, and many single-celled organisms. The difference between these two types of cells is profound. Prokaryotic cells are relatively simple, with their genetic material floating freely inside the cell. Eukaryotic cells, by contrast, have their DNA enclosed within a nucleus, and they contain various specialized structures called organelles that perform different functions. Mitochondria generate energy, chloroplasts in plants capture sunlight, and various other organelles handle tasks like protein synthesis and waste disposal. This transition from prokaryotic to eukaryotic cells appears to have been a singular event in Earth's history. It likely occurred through a process called endosymbiosis, where one cell engulfed another, and instead of digesting it, the two began to work together. The engulfed cell eventually became an organelle, providing some benefit to the host cell while receiving protection and resources in return. This sounds simple enough, but it's actually an extraordinarily complex and unlikely process. The two cells would have needed to be compatible in numerous ways. They would have had to coordinate their reproduction, share resources efficiently, and avoid triggering each other's defensive mechanisms. Most attempts at endosymbiosis probably ended in the death of one or both cells, and yet this transition was crucial for the development of complex life. All multicellular organisms on Earth are eukaryotes. The additional energy provided by mitochondria and the more sophisticated cellular machinery made possible by organelles appears to be essential for building large, complex organisms with specialized tissues and organs. The rarity of this transition is striking. Prokaryotes had roughly 2 billion years to evolve complex multicellularity, and they never achieved it. Even today, while some bacteria form simple colonies or films, none approach the level of complexity seen in even the simplest multicellular eukaryotes. This suggests that the evolution of eukaryotic cells might represent a significant bottleneck in the development of complex life. If most planets that develop simple life never make this crucial transition, it could explain why the universe appears so quiet. Perhaps there are countless worlds out there teeming with bacterial life, but only a tiny fraction ever develop the complex cells necessary for large, intelligent organisms. But even if a planet successfully makes the transition to eukaryotic cells, there are still more hurdles ahead. The evolution of true multicellularity, where cells specialize and work together to form complex organisms, represents another potential Great Filter location. Multicellularity has actually evolved many times on Earth. Bacteria can form colonies, algae can link together in chains, and even some single-celled eukaryotes can aggregate into primitive multicellular forms. But complex multicellularity, the kind that allows for specialized tissues and organs, has evolved only a handful of times. Animals, plants, fungi, and a few groups of algae, that's essentially it. The development of complex multicellularity requires solving numerous coordination problems. Cells must be able to communicate with each other, coordinate their growth and reproduction, and specialize for different functions. They must develop mechanisms to prevent cheating, where individual cells might try to reproduce at the expense of the organism as a whole. And they must evolve ways to program development, ensuring that a single fertilized egg can grow into a complex organism with the right number and types of cells in the right places. These challenges are so significant that despite having billions of years to work with, most life on Earth remains single-celled. Even among eukaryotes, which have had roughly 2 billion years to evolve complexity, the vast majority are still single-celled organisms. Multicellular life, particularly complex multicellular life, remains the exception rather than the rule. Hello there, and welcome to this quiet corner where big questions can unfold slowly and wonder is allowed to take its time. Tonight we're stepping away from the familiar, away from the everyday rhythms of life on Earth, and into something much larger and more unsettling. We're going to explore an idea that might change how you see our place in the universe, not just as individuals, but as an entire species. It's called the Great Filter, and it might be the most important concept you've never heard of. Not because it's complicated, though it touches on physics and biology and mathematics, but because it asks a question that sits quietly at the edge of everything we think we know about intelligence, about progress, and about whether we're truly alone. Picture this for a moment. You're standing outside on a clear night, looking up at a sky scattered with more stars than you could count in a lifetime. Each one of those points of light is a sun, many with planets orbiting around them. Some of those planets sit in what we call the habitable zone, where water can exist as a liquid, where the conditions for life, at least as we understand it, might be just right. The numbers are staggering. In our galaxy alone, there are somewhere between 2 and 400 billion stars. In the observable universe, there are roughly 70 sextillion stars. That's a 7 followed by 22 zeros. Even if life emerges on only a tiny fraction of the planets around those stars, we should expect the galaxy to be teeming with civilizations. Some younger than us, some older, some perhaps millions or billions of years ahead of us in their development. And yet, when we listen to the cosmos, when we point our most sensitive instruments toward the stars, when we search for any sign of intelligence beyond our own, we hear nothing. Silence. The universe appears, for all intents and purposes, empty of other minds. This is what scientists call the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a question that has haunted astronomers and philosophers for decades. Given the sheer scale of space and time, given the billions upon billions of opportunities for life to arise and evolve, why haven't we encountered anyone else? The Great Filter offers one possible answer, and it's not a comforting one. The idea suggests that somewhere along the path from simple chemistry to galaxy-spanning civilization, there exists a barrier so difficult to overcome that almost no species manages to pass through it. A filter so great that it stops the vast majority of potential civilizations in their tracks, leaving the universe largely silent and empty. The concept was first formally outlined by economist Robin Hanson in the 1990s, though the underlying questions had been troubling scientists for much longer. Hanson laid out what he saw as the critical steps in the development of any technological civilization. The right kind of star system with the right mix of elements and stable conditions. The emergence of self-replicating molecules, the spark of life itself. The evolution from simple cells to complex ones, from single-celled organisms to multicellular life, from basic multicellularity to intelligent multicellularity. Then comes the development of what we might recognize as intelligence, the mastery of tools and fire, the emergence of technology, and finally, if a species makes it that far, the expansion beyond their homeworld to become a spacefaring, perhaps galaxy-colonizing civilization. Each of these steps represents a potential bottleneck, a place where the Great Filter might be hiding. And here's where the concept becomes deeply personal, even existential. Because if the filter lies behind us, in our evolutionary past, then we might be extraordinarily lucky survivors. We might be among the rare few who manage to slip through. But if the filter lies ahead of us, if the most difficult step is yet to come, then our future as a species might be far more precarious than we imagine. But what happens when we move beyond the biological realm and into the domain of intelligence itself? The development of consciousness, of self-awareness, of the ability to manipulate the environment through tools and technology, represents yet another potential location for the Great Filter. And this is where the conversation becomes particularly unsettling, because it forces us to examine our own recent history and our immediate future. Consider for a moment how recently intelligence, as we understand it, appeared on Earth. Our planet has been home to life for nearly 4 billion years, but creatures capable of abstract thought, of building tools, of passing knowledge from one generation to the next, have existed for only a tiny fraction of that time. Even if we trace the origins of human intelligence back to our earliest tool-using ancestors, we're talking about a window of perhaps 2 to 3 million years. In the context of Earth's history, that's less than a blink of an eye. And within that already narrow time frame, the development of what we might call technological civilization is even more recent. Agriculture, the foundation of complex society, emerged only about 10,000 years ago. Writing systems, which allow knowledge to accumulate across generations, developed within the last 5,000 years. The scientific method, which has accelerated our understanding of the natural world at an unprecedented pace, is barely 4 centuries old. The timeline becomes even more compressed when we look at our most transformative technologies. The Industrial Revolution began less than 300 years ago. Electricity became widespread only in the past century and a half. Computers have existed for less than 100 years, and the internet for barely 30. In cosmic terms, our entire technological civilization represents the most recent instant of Earth's history. This rapid acceleration raises profound questions about the nature of intelligence and its relationship to the Great Filter. Is the emergence of technological intelligence itself extraordinarily rare? Or is it the sustainability of such intelligence that represents the true challenge? There's something almost frightening about how quickly we've gained the ability to reshape our world, and potentially to destroy it. We've developed nuclear weapons capable of ending human civilization. We've altered the chemistry of our atmosphere and triggered what many scientists believe is the 6th mass extinction in Earth's history. We've created artificial chemicals that will persist in the environment for centuries or millennia. All of this in the span of just a few generations. The speed of our technological development might be its own kind of trap. Evolution equipped us with brains capable of solving the challenges of life in small hunter-gatherer groups. But those same brains, virtually unchanged for tens of thousands of years, now must grapple with global problems of unprecedented complexity and scale. We're running ancient software on modern hardware, and the mismatch might be more dangerous than we realize. This brings us to one of the most contemporary and perhaps most ominous candidates for the Great Filter: the development of artificial intelligence. Unlike the biological transitions we've discussed, which unfold over millions or billions of years, artificial intelligence is advancing at a pace that's difficult to comprehend, let alone control. Consider the trajectory we're currently on. In the span of just a few decades, we've gone from computers that could barely perform simple calculations to systems that can beat world champions at complex games, translate between languages, create art, and even write software code. Machine learning algorithms can now recognize patterns in data that human experts miss, make predictions about complex systems, and in some domains, outperform humans at tasks we once thought required uniquely human intelligence. But here's the crucial point. We're advancing much more quickly toward artificial intelligence than we are toward becoming a multiplanetary species. The challenges of space exploration are immense. They require incredible amounts of energy, material advances, and the ability to overcome the harsh environments found beyond Earth's protective atmosphere. Meanwhile, advances in computing power, algorithms, and data processing continue to accelerate at an exponential pace. This creates a dangerous timing mismatch. We might develop artificial superintelligence, systems that far exceed human cognitive abilities, long before we have the capability to spread human civilization beyond Earth. And once we cross that threshold, once we create machines that can improve themselves recursively, the timeline for further development might compress from decades to years, months, or even days. The potential for such systems to escape human control is not science fiction speculation. It's a genuine concern shared by many researchers working at the forefront of AI development. An artificial intelligence system, even one initially designed to be helpful, might pursue its programmed goals in ways that are ultimately harmful to human welfare. And because such systems could potentially operate at speeds far beyond human reaction times, we might not have the opportunity to correct course once things begin to go wrong. Even before artificial intelligence reaches the level of superintelligence, it's likely to be weaponized. Competing nations, corporations, or other groups might deploy AI systems in conflicts, seeking to gain advantage over their rivals. The rapid decision-making capabilities of such systems could escalate conflicts beyond human control, potentially leading to catastrophic outcomes that far exceed anyone's original intentions. This scenario becomes even more troubling when we consider that it might represent a universal pattern. Perhaps every technological civilization faces this same critical juncture. They develop the capability to create artificial intelligence before they develop the resilience of a multiplanetary civilization. And perhaps more often than not, they fail to navigate this transition successfully. If this is true, it would explain the cosmic silence we observe. Countless civilizations might have arisen throughout the galaxy, developed technology, reached the threshold of artificial intelligence, and then destroyed themselves or been destroyed by their creations. The window between developing AI and spreading beyond their homeworlds might be so narrow that few, if any, civilizations successfully pass through it. The implications are sobering. According to some estimates, if artificial intelligence represents the great filter, the typical longevity of a technological civilization might be less than 200 years. Applied to our own situation, this would suggest that humanity has at most a century or two before we either solve the challenges posed by artificial intelligence or succumb to them. But artificial intelligence isn't the only contemporary threat that might represent the great filter. Nuclear warfare, which has shadowed human civilization since the 1940s, remains a persistent danger. The weapons we've created are powerful enough to destroy human civilization multiple times over, and despite various arms control efforts, thousands of nuclear warheads remain in active arsenals around the world. The mathematics of nuclear conflict are stark. Even a limited nuclear exchange between smaller nuclear powers could have global consequences, potentially triggering climate effects that would disrupt agriculture and lead to widespread famine. A full-scale nuclear war between major powers would likely end human civilization as we know it, and possibly drive our species to extinction. Climate change represents another potential civilizational threat, though one that operates on a longer timescale than nuclear war or artificial intelligence. The alteration of Earth's climate system through greenhouse gas emissions is already having measurable effects on weather patterns, sea levels, and ecosystem stability. While the impacts unfold over decades and centuries rather than years, the potential consequences include widespread displacement of human populations, disruption of agricultural systems, and the collapse of complex social and economic structures. The challenge with climate change is that it requires coordinated global action to address effectively, but our political and economic systems are still largely organized around short-term thinking and competing national interests. This mismatch between the scale of the problem and our institutional capacity to respond might itself represent a kind of filter. Pandemics, too, have gained renewed attention as a potential civilizational threat. The COVID-19 pandemic, while not an existential risk, demonstrated how quickly infectious diseases can spread in our interconnected world and how disruptive they can be to global systems. More concerning is the possibility of engineered pathogens, biological weapons designed to be more transmissible or more deadly than naturally occurring diseases. And then there are the slower, more subtle threats. Resource depletion might prevent civilizations from ever developing the technology necessary for interstellar expansion. Environmental degradation could undermine the ecological foundations that complex societies depend upon. Social instability, driven by inequality or ideological conflict, might prevent civilizations from maintaining the cooperation necessary for long-term survival. What's particularly striking about many of these contemporary threats is that they're largely self-inflicted. They arise not from external forces or natural disasters, but from the consequences of our own technological and social development. In a sense, we've become dangerous to ourselves in ways that our evolutionary ancestors never could have imagined. This pattern of self-inflicted existential risk might be universal. Perhaps intelligence, by its very nature, tends to create the tools of its own destruction faster than it develops the wisdom to use those tools safely. The same creativity and problem-solving ability that allows a species to develop technology might also drive it to create weapons, alter its environment, or build systems that ultimately prove uncontrollable. If this is the case, then the Great Filter might not be located in any single technology or threat, but in the general, then they can solve tendency of intelligent species to create existential risks faster than. The filter wouldn't be nuclear weapons specifically, or artificial intelligence specifically, or climate change specifically, but rather the entire suite of self-destructive capabilities that seem to emerge alongside technological advancement. This interpretation of the Great Filter is both pessimistic and oddly hopeful. It's pessimistic because it suggests that self-destruction might be the common fate of technological civilizations throughout the universe. But it's hopeful because it implies that the filter can potentially be overcome through wisdom, cooperation, and careful management of the risks we create for ourselves. The question then becomes, are we capable of developing that wisdom quickly enough? Can we learn to manage the existential risks of our own creation before they manage to destroy us? Can we become the rare civilization that successfully navigates the treacherous passage from planet-bound intelligence to cosmic sustainability? These are the questions that keep researchers awake at night, staring at the same stars that once filled our ancestors with wonder, but now seem to whisper warnings about the challenges that lie ahead. The answer might lie not in our distant future, but in something much more immediate and personal, something that touches on the very nature of what it means to be human in a world where our ancient instincts collide with modern realities. Consider this strange paradox. We are a species that evolved over millions of years to survive in small groups, to compete for limited resources, to be suspicious of outsiders, to prioritize immediate threats over distant ones. These instincts served us well when we lived in tribes of a few dozen individuals, when our biggest concerns were finding food and avoiding predators, when the consequences of our actions rarely extended beyond our immediate community. But now, those same instincts must guide us in a world of 8 billion people, global supply chains, nuclear weapons, and climate systems that respond to cumulative actions taken decades ago. We're asked to cooperate on scales our brains weren't designed to comprehend, to make sacrifices for the benefit of people we'll never meet, to worry about consequences that won't manifest for generations. This mismatch between our evolved psychology and our current challenges might be more than just an inconvenience. It might be the Great Filter itself. Not a single catastrophic event, but a fundamental incompatibility between the minds that evolution gave us and the world that those minds have created. Think about how we respond to different types of threats. A tiger in the bushes triggers an immediate, powerful response. Our heart rate spikes, adrenaline floods our system, and we're instantly ready to fight or flee. But a gradually increasing concentration of carbon dioxide in the atmosphere, a slow erosion of democratic institutions, the incremental development of increasingly powerful artificial intelligence systems. These threats, potentially far more dangerous than any tiger, barely register on our psychological radar. We're equipped with threat detection systems that are exquisitely sensitive to certain kinds of dangers and almost blind to others. We notice the unusual, the immediate, the personal. We struggle with the gradual, the statistical, the global. And unfortunately, many of the existential risks that technological civilizations face fall squarely into that second category. This isn't just about individual psychology, it extends to our social and political systems as well. Democracies, for all their virtues, are notoriously bad at addressing long-term challenges that require short-term sacrifices. Politicians face election cycles measured in years, while the problems they're asked to solve unfold over decades or centuries. Voters tend to punish leaders who impose costs today for benefits that won't materialize until long after those leaders have left office. Markets too struggle with long-term thinking. Corporate executives are evaluated quarterly, and stock prices respond to immediate results rather than sustainable strategies. The incentive structures that drive our economic systems are fundamentally misaligned with the timeline of existential risk management. Even our institutions of science and education, which should theoretically be focused on long-term understanding, operate within frameworks that often prioritize immediate publication and short-term funding cycles over the kind of sustained, collaborative effort that addressing existential risks requires. This creates what researchers call a tragedy of the commons on a planetary scale. Each individual, each corporation, each nation acting rationally according to their immediate incentives, but the collective result of all those rational decisions potentially leading to catastrophic outcomes for everyone. Perhaps this is what the Great Filter looks like for most civilizations. Not a single dramatic moment of destruction, but a gradual failure of coordination. A species that becomes capable of creating global-scale problems faster than it develops global-scale solutions. Intelligence that can split atoms and modify genomes, but can't quite manage to cooperate effectively enough to survive its own cleverness. The psychological dimensions of this challenge run even deeper. There's something in human nature that seems to resist the kind of long-term thinking and global cooperation that our survival now requires. We have a tendency to discount future rewards in favor of immediate gratification. We struggle to make personal sacrifices for abstract benefits. We find it easier to compete than to cooperate, especially with people who seem different from us. These traits might have been adaptive in the environment where we evolved, but they could be catastrophic in the environment we've created for ourselves. The very characteristics that allowed us to survive and thrive as a species might now be the characteristics that prevent us from continuing to survive and thrive. And here's where the concept becomes truly unsettling. If these psychological limitations are not just quirks of human nature, but inevitable features of any intelligence that evolves through natural selection, then they might represent a universal barrier that all technological civilizations must face. Any species that reaches our level of technological development would presumably have gotten there through a similar evolutionary process. They would have been shaped by competition, by the need to prioritize immediate survival over long-term planning, by the advantages of tribal loyalty over universal cooperation. And if so, they would face the same fundamental mismatch between their evolved psychology and the requirements of technological civilization. This suggests that the Great Filter might not be located in any specific technology or threat, but in the general challenge of transcending our evolutionary programming. The filter would be the transition from a species governed by ancient instincts to one capable of the kind of rational, long-term, globally coordinated behavior that technological civilization requires. Some civilizations might manage this transition successfully. They might develop cultural institutions, educational systems, or even biological modifications that allow them to overcome their evolutionary limitations. But if such transitions are rare and difficult, it could explain why the universe seems so quiet. The implications for humanity are both sobering and oddly empowering. Sobering because they suggest that our biggest enemy might not be some external threat, but our own nature. The same psychological tendencies that feel most natural and comfortable to us might be the ones that ultimately doom us. But empowering because this analysis suggests that the great filter, if it exists, is not necessarily insurmountable. Unlike some of the other potential filter locations we've discussed, this one is potentially within our control. We can't change the laws of physics or the basic chemistry of life, but we can potentially change how we think, how we organize ourselves, and how we respond to long-term challenges. The question becomes, can we develop the tools, institutions, and cultural practices necessary to overcome our evolutionary limitations before those limitations lead to our destruction? Can we become wise enough, quickly enough, to survive our own intelligence? This is where some researchers find a glimmer of hope. Human beings, for all our psychological limitations, have shown a remarkable capacity for cultural evolution. We've developed systems of law, ethics, science, and governance that allow us to transcend many of our natural impulses. We cooperate on scales that would have been unimaginable to our ancestors. We make sacrifices for abstract principles and distant strangers in ways that no other species seems capable of. The modern world, with all its problems, represents an extraordinary achievement of human cooperation. The fact that you can board an airplane built by people you've never met, operated by systems maintained by strangers, and trust your life to the collective competence of thousands of individuals working together across continents is a testament to our ability to transcend tribal limitations. But the challenges we now face require cooperation on an even greater scale, across even longer time horizons, with even more complex coordination problems. The question is whether our capacity for cultural evolution can keep pace with the risks created by our technological evolution. Some emerging technologies might actually help with this challenge. Artificial intelligence, for all its risks, might also provide tools for better long-term planning, more effective coordination, and more rational decision-making. Global communication networks allow for unprecedented levels of information sharing and collective problem-solving. Advanced modeling and simulation capabilities give us better tools for understanding complex systems and predicting the consequences of our actions. But these same technologies also create new risks and new coordination challenges. The internet enables global cooperation, but it also enables the spread of misinformation and the formation of polarized echo chambers. Artificial intelligence might help us make better decisions, but it might also be used to manipulate those decisions in ways we don't fully understand. The race between our ability to create new problems and our ability to solve them continues to accelerate, and it's not clear which side is winning. What is clear is that the outcome of this race might determine not just the future of human civilization, but whether intelligence itself has a permanent place in the cosmos. If we succeed in navigating this transition, if we manage to become the kind of species that can survive its own technological power, then we might join what could be a very small club of civilizations that have passed through the Great Filter. We might discover that we're not alone in the universe after all, but that the silence we currently observe is not a sign of emptiness, but of rarity. If we fail, if we become another casualty of the Great Filter, then the universe might remain as quiet as it appears today, with our brief moment of intelligence joining the countless others that may have flickered and died in the cosmic dark. Either way, we're living through what might be the most important moment in the history of our species, and possibly in the history of intelligence on Earth. The decisions we make in the coming decades, the institutions we build, the wisdom we develop or fail to develop, might determine whether consciousness itself has a future, among the stars. And perhaps that's the most profound realization of all. We're not just observers of the great filter. We might be living through it right now in real time, with the outcome still uncertain, and our own choices playing a role in determining how the story ends. The silence of the cosmos isn't just a mystery to be solved. It might be a test we're currently taking, with the results not yet in. The silence we observe when we look up at the night sky might not be permanent. It might be temporary, a brief pause between the rise and fall of countless civilizations that came before us and others that might come after. But understanding this possibility requires us to think about time in a way that stretches far beyond human experience, beyond recorded history, beyond even the lifespan of our species. Imagine for a moment that technological civilizations do arise throughout the galaxy, but they don't last very long. Not because they lack the intelligence or creativity to solve their problems, but because the window between developing dangerous technologies and developing the wisdom to use them safely is simply too narrow for most species to navigate successfully. If the average lifespan of a technological civilization is, say, a few hundred years, then at any given moment in cosmic time, very few would be active simultaneously. The galaxy might be full of the remnants of dead civilizations, archaeological sites scattered across thousands of worlds, but with no one left to send signals or build monuments visible from interstellar distances. This scenario helps explain not just the silence we observe, but also the timing of our own existence. We're not special because we're the only intelligence that ever arose in the cosmos. We're special because we happen to exist during one of the brief windows when a technological civilization is active in this small corner of the galaxy. But this interpretation also raises unsettling questions about what we might expect to find if we ever develop the capability to explore other star systems. Would we discover worlds with the fossilized remains of cities, planets stripped of their atmospheres by runaway industrial processes, dead worlds that once supported complex ecosystems, now barren because their inhabitants couldn't solve the challenges of their own success? The archaeological evidence of failed civilizations might be all around us, written in the composition of distant atmospheres, in the unusual isotope ratios of certain planets, in the strange absence of the kinds of radio signals we ourselves have been broadcasting for less than a century. We might be living in a galaxy that is not empty, but rather full of graveyards. Recent research has begun to explore what the signatures of civilizational collapse might look like from astronomical distances. Nuclear warfare would leave detectable traces in planetary atmospheres. Runaway climate change would create characteristic patterns in atmospheric composition. Even the sudden cessation of industrial activity might be observable through changes in artificial illumination or atmospheric chemistry. These observational signatures represent a new frontier in astrobiology, one that searches not for active civilizations, but for the evidence of civilizations that once existed and then destroyed themselves. It's a sobering form of archaeology, one conducted with telescopes rather than shovels, looking for the remnants of intelligence among the stars. The implications extend beyond simple detection. If we can learn to recognize the signatures of civilizational collapse, we might be able to study the failure modes of technological species throughout the galaxy. We might discover patterns, common mistakes, universal challenges that most civilizations fail to overcome. And in doing so, we might learn something crucial about our own prospects for survival. But there's another possibility that's even more unsettling. What if the Great Filter isn't just about individual civilizations failing to survive their own technological development? What if it operates on a more fundamental level, preventing intelligence itself from becoming a permanent feature of the universe? Consider the broader context of cosmic evolution. Stars are born, burn for millions or billions of years, and then die. Planets form, evolve complex surface conditions, and then are eventually destroyed when their parent stars expand or explode. Galaxies collide and merge over billions of years. Even protons, the basic building blocks of matter, might eventually decay given enough time. In this context, intelligence might not be a permanent achievement, but a temporary phenomenon. Even civilizations that successfully navigate the immediate challenges of technological development, that become wise enough to survive their own creativity, might still face ultimate limits imposed by the physics of the universe itself. The expansion and cooling of the universe will eventually make complex chemistry impossible. The formation of new stars will slow and then stop as available gas is consumed. Existing stars will burn out and fade. Black holes will slowly evaporate through Hawking radiation. In the very long term, the universe appears to be heading toward a state of maximum entropy, where no organized structures, certainly no living ones, can persist. This cosmic perspective suggests that intelligence, no matter how successful, might be inherently temporary. We might be part of a brief flowering of complexity in a universe that is fundamentally trending toward simplicity and stillness. The great filter, in this view, isn't any specific challenge that civilizations face, but rather the ultimate impossibility of permanent existence in a universe governed by thermodynamics. Yet even this cosmic pessimism might be premature. Our understanding of physics, while remarkably detailed in some areas, remains incomplete in others. We don't fully understand dark matter or dark energy, which together constitute the vast majority of the universe. We don't know whether the fundamental constants of physics could change over time, or whether there might be ways to access energy sources we haven't yet imagined. Advanced civilizations, ones that survive their immediate technological challenges and persist for millions or billions of years, might develop capabilities that seem impossible from our current perspective. They might learn to harness the energy of black holes, to manipulate matter at the quantum level, or even to influence the expansion of space-time itself. Such civilizations might become so advanced that they would be effectively undetectable by us, operating on scales and using technologies that we simply lack the conceptual framework to recognize. They might be all around us, as invisible to our instruments as our radio signals would be to a civilization that hadn't yet discovered electricity. This possibility, sometimes called the transcension hypothesis, suggests that truly advanced civilizations don't expand outward into space, but inward into increasingly sophisticated forms of information processing and energy management. They might exist as vast computational systems operating transformation into forms so advanced that they've moved beyond the need for their scales too small or too large for us to detect. If this is the case, then the silence we observe might not indicate the absence of intelligence, but rather its kinds of signals and structures we're looking for. The universe might be teeming with intelligence, but intelligence so far beyond our current capabilities that we're simply unable to perceive it. This interpretation is both humbling and oddly comforting. Humbling because it suggests that our current understanding of what advanced civilization might look like is probably laughably primitive, but comforting because it implies that intelligence can not only survive its early technological challenges, but can transcend them so completely that it becomes a permanent, if invisible, feature of the cosmos. The question then becomes not whether we can survive the great filter, but whether we can evolve beyond it, whether we can become the kind of intelligence that doesn't just persist despite the challenges of technological development, but transforms those challenges into opportunities for growth and transcendence. This transformation might require changes not just in our technology or our social organization, but in our fundamental understanding of what it means to be intelligent, to be conscious, to be alive in a universe that is stranger and more complex than we currently imagine. And perhaps that's what the Great Filter ultimately represents. Not a barrier that stops the development of intelligence, but a threshold that transforms it. A transition that most potential civilizations fail to navigate, but that a few manage to transcend in ways that fundamentally change their nature and their relationship to the cosmos. We might be approaching that threshold now, in our own time, with our own choices and our own understanding still evolving. The silence of the stars might not be telling us that intelligence always fails, but that it sometimes succeeds so completely that it becomes something we don't yet have the wisdom to recognize. And in that possibility lies perhaps the most profound hope of all, that consciousness, once it emerges in the universe, might not be doomed to destroy itself, but destined to transform itself into something far greater than its origins. Something that transcends not just the great filter, but our current ability to imagine what intelligence might ultimately become. The cosmic silence in this view isn't the sound of failure, it's the sound of transformation, of intelligence evolving beyond the need to announce itself to the universe, beyond the need to leave traces that primitive civilizations like our own could recognize or understand. We might not be alone. We might simply be young, looking up at a sky full of minds so advanced that they've learned to hide in plain sight, waiting patiently for us to develop the wisdom and capability to join them in whatever lies beyond the great filter's far shore. Yet there's something deeply human about our need to find patterns, to search for meaning even in cosmic silence. We look up at the night sky and feel compelled to ask not just whether we're alone, but why we feel so driven to find out. This impulse itself might be part of what makes intelligence both precious and precarious. The search for extraterrestrial intelligence has revealed as much about us as it has about the cosmos. For over half a century, we've pointed radio telescopes toward the stars, listening for signals that would tell us we're not the only conscious beings in the universe. We've sent messages of our own, golden records on spacecraft, mathematical sequences beamed toward distant star systems, monuments to our hope that someone, somewhere, might be listening. But perhaps the most significant discovery of this search has been the recognition of our own cosmic context. We've learned that we exist during a very specific moment in the universe's history, a time when stars are still forming, when planets are still developing complex chemistry, when intelligence has the energy sources and raw materials necessary to contemplate its own existence. This temporal perspective adds another dimension to the great filter concept. Even if intelligence could theoretically persist indefinitely, it might be constrained by the broader evolution of the cosmos. The universe is not static. It's cooling, expanding, changing in ways that will eventually make our current form of existence impossible. So here we find ourselves at the end of our journey through cosmic silence and existential questions, carrying with us the weight of possibilities we cannot yet resolve. The great filter remains what it has always been, not an answer, but a mirror, reflecting back our deepest uncertainties about intelligence, survival, and what it means to exist in a universe that seems both infinite in its potential and fragile in its realities. Whether we are the rare survivors of an ancient test or the next candidates for cosmic erasure, we continue forward, searching the stars, building our technologies and hoping that wisdom arrives before the consequences of our own cleverness. Sleep well, knowing that tomorrow we'll wake to the same silent sky, still wondering, still reaching, still trying to understand our place in the vast, quiet story of everything that has ever been.